So, next we see what is a tap controller. So, tap controller it is basically controlling all other modules in the boundary scan, and you see that okay, it has got a number of states. So, there are 16 states in this tap controller. So, it works on this test clock TCK and this TMS, okay, and it outputs 9 or 10 signals included in clock DR, update DR, shift DR. So, all these signal values will be updated as it passes through the states. So, this is basically the state transition diagram of this tap controller. So, we will try to understand a part of it. So, this test logic reset. So, when this test logic reset is pressed, so this whole thing gets reset and it comes to the state 1. It comes to the state test logic reset. Now, you see that whenever it is whenever this is mode this the test logic reset, whenever this particular pin is pressed, so this will be coming to this. Similarly, when this is basically that after that this test mode signal, if it is 0, so it will come to this test run test idle cycle, and it will remain for the in this state as long as this TMS input is 0, and from this run or test idle. So, if the TMS input is 1, so it comes to this particular state. So, it select data register scan, then it goes to, if it now these transitions are on the TMS line. So, if TMS line, if it is 0, then it will go to the capture data register, then if it is 0, then it will again go to shift data register. As long as it is 0, so it is remaining in the shifting mode, and then in 1, so it is exiting the data register, exiting this actually the shifting operation is exited. Now, there can be a pause. So, you can put this TMS value at 0. So, as long as this is 0, so it will remain in the pause mode. Now, if it is 1, then it comes to another state where exit to DR. So, basically this is basically the updation of the input from the circuit. So, for the exit 1, pause, and this exit 2. So, they are actually taking they are actually doing the that launching mode, or the pattern is getting applied to the circuit, and then after that again they are, if it is 0, then again it will go to the next shift DR, so that the next pattern will be shifted in. So, this way this part is responsible for doing the shifting of test pattern, applying the test pattern, etc. Now, whenever if you give a 1 signal TMS equal to 1, that means we want to update the other register R2. So, this update data register takes place on this. So, if it is 1, then it, and if it is 1, it goes to this state, again select the data register scan and all that. If it is 0, then it goes to the idle, as if this no more testing has to be done. So, it will remain idle. Again if the TMS is 1, so it will again go into the data register scan mode. Now, in the select data register scan mode, so if you give this input as 1, then it will go to the instruction register update. Basically, in this part it was shifting in the test pattern, getting the responses, updating the boundary scan cells and all that. So, that was taking part here. So, this is basically the data register updation, and sometimes we need to update the other part, the instruction register update and all that. So, that is done by putting 2 TMS high for 2 successive cycles. So, TMS is high for 2 successive cycles from the run test idle mode, it will come to this instruction register mode. So, it is select IR scan. So, it will select the instruction register, then if it is 1, so it will go back to the test logic reset state. If it is 0, it will capture the instruction register. So, it will the whatever value is coming on the TDI line, so that will be captured into this instruction register. Then this shift IR, so this will, the successive bits will be of the TDI, so they will be shifted here. Then we have got exit 1 IR, so exit, pause. So, this is actually for applying the instruction that we have got here. So, we want to decode it. So, that decoding is done at the decoding time is given here. Then there is update instruction register mode, so where it will be doing the updation. So, a full description of this will be available in 1149 manual, but these are actually, this shows that this TAP controller, it goes via a number of states, and by controlling this TMS signal we can control the transition of this TAP controller. so that it can make the either the test pattern to pass into the boundary scan register cells, or it can update the internal registers, okay, for various other things. Okay. So, other control related instructions that needs to be updated, that can be taken into the instruction register and other registers. So, these are the major functions that are provided by the tap controller, the resetting the boundary scan circuitry, then load instructions into instruction register, perform test capture operation, perform test update operation, and shift test data in and out. So, these are the major functions to be provided by the tap controller. So, these are the various states that we have listed previously. So, test logic reset, so that is the normal mode. So, basically the tap controller will remain in this mode in most of the time. So, there is no function of the boundary scan cell register, no testing is going on. So, no data needs to be transferred to the boundary scan registers. Then this run test idle, so wait for internal tests such as BEAST. So, run test idle means the test has been initiated, and now when the test will be over, then it should be informed. So, that way it waits for the internal test to be over, such as BEAST. Then this select DR scan, so it initiate a data scan sequence. So, in this DR scan, so you see the run test idle is it is some internal test is going on. Then this select DR scan means it is some data register scan operation is going to start. So, that is the select DR scan. Then the capture DR load test data in parallel. So, this capture DR is coming from this is so capture DR mode. So, if this bit TMS bit is 0, so it is coming to capture DR. So, this is coming from the from that circuit as the capture input. So, from the inline that we have, so that will be put into the DR register. So, that is the into the R1 register. So, that is load test data in parallel. Then the shift DR, so it is the from the TDI line or the serial input line. So, if we are trying to load the data, so then the shift DR state will come, load data in series. Then exit 1 DR, so it finish phase 1 shifting of data. So, first phase of shifting data is over. Now, there is some other operation has to be done, because the maybe the test pattern will be applied and the response will be captured, things like that. So, you need to store wait for some time. So, that is basically the pause DR operation. So, temporarily hold the scan operation. So, for example, allow the bus master to reload data. Bus master will reload data means the pattern will be applied to the circuit and the response will be available on the bus. So, that way it will be there. Then this exit to DR, so it finish phase 2 shifting of data. So, here actually the response will be of current pattern will be going out, and then that is the phase exit 2. And there is update DR, so parallel load from associated shift registers. So, this is this update DR. So, this is basically from the shift register, the parallelly the values will be updated. So, controls for IR are similar to those for DR. So, you as I was showing you that okay, so this entire operation is divided into 2 segments. In one segment we are updating the data register, doing some operation of the data register. Another part we are updating the instruction register and the related operations. So, they are going to be similar, the philosophy of operation is similar, only in one case the boundary scan register that gets updated, and in another case this instruction register and other related places they get updated. Now, what are the instructions that this tap controller can support? First instruction is a bypass operation. So, it bypass data through a chip. So, this is a bypass operation. Then there is a sample operation. So, that will sample or capture the test data into the boundary scan register. Then there is a preload. So, shift in test data and update the boundary scan register. Then there is an X test mode, where the test interconnection between chips of a board, so that they will be tested. And there is an optional in test run beast clamp ID code, then user code high z. So, these are some optional instructions, but these are the 4 basic instructions that are to be supported for a board level testing. So, bypass, this is required because you can bypass a chip if the next instruction is not meaningful, instruction or data is not meaningful for this particular chip. So, you can bypass it, putting it into bypass mode. So, sample mode. So, this is basically to get the basically getting the test data, the captured data into the boundary scan register. Then preload, basically shifting in the test data. So, that is there, and X test is basically for testing interconnect between the boards. So, there is a difference between testing a chip and testing an interconnect. So, testing a chip means there we are willing to apply the particular pattern to the inputs of the chip, but when we are trying to test the interconnect, so output of one chip connects to the input of another chip. So, as a result, the test pattern actually goes to the output of the chip and it is captured at the input of the second chip, which is counter of what we do for chip testing, where the input is applied to the input of the chip and output is collected from the output pin of the chip. So, it is, so that is why it is called an X test mode. Okay. So, naturally there has to be something called an in test mode, where the pattern is applied to the chip for testing. So, that is but it may not be there, like this capture mode automatically may take care of that. Run BIST. So, if the chip is BIST fitted, then this run BIST mode is useful. Then clamp. So, it will take the value at a particular point. So, we will see them. So, how this bypass instruction is executed? So, in the bypass instruction mode, so the instruction register gets that bypass instruction, and then this tap controller will select this multiplexer in such a fashion that whatever is coming in TDI is going to the TDO, and this bypass register is a 1 bit register. So, it will introduce a delay of only 1 unit through the chip. So, instead of having a delay of equal to all these sum of all these boundary scan cells, so it will have a delay of only 1 bit to get the input transferred from TDI to the TDO line. Okay. So, that is the bypass instruction. Then the sample instruction. So, sample instruction. So, what is happening? First, this the input line, which is the functional input. So, that is going to this multiplexer, and then this this is also coming to this R1 register. Now, this multiplexer, through this multiplexer, it is selecting the it is applied to the internal logic. So, this R2 is not connected to this is multiplexer is programmed in such a fashion that this input goes to the internal logic. So, the result is available at this point. Now, this result is coming to the this multiplexer and available at the output. At the same time, this result is also available at the R1 line here, the R1 register of this cell. So, you see that the input has been captured here and this output has been captured at this point. So, that is the sample operation. So, by application of a particular input, what happens to the output? So, that is captured in the R1 line, R1 register. Then there is a preload instruction. So, in a preload instruction, this whatever is coming through this TDI line, so that is loaded into this register, and that is also loaded into this R1 register, but the functional input is functional part goes unaltered, like this internal input. So, it is loaded in through this multiplexer. The multiplexer is selecting this input line. So, it operates functionally, that the internal logic or the logic part of the circuit. So, it operates in its normal mode, but this through this TDI line we can preload some pattern onto these boundary scan cells. Okay. So, this R1 R2 registers. So, we can preload some pattern. So, that is the preload instruction. Then this X test instruction. So, what is done first? So, X test I have said that it will be testing the interconnect between the chips, like we are interested to check say this particular interconnect. Then how can we test this thing? First of all, this test data input that we want to apply at this point, maybe we want to check whether this line is stuck at 1 or not. So, we have to send a 0 onto this line. So, that 0 bit is shifted through this TDI line like this. So, there is the chip 1, it operates in the shift data register mode, and chip 2 does not have to do anything. So, it is not yet working in the test mode. So, it is working in the normal mode. So, this bit through a number of shifting. So, it comes to this point. Then in the second step, this chip 1 is put into update DR mode. So, in the if we put into the update DR mode, then you know that when this shifting was going on, so it was only affecting the R1 register. So, this R1 register was only getting affected. So, it was not available on the R2 register. So, this was so at the output side. So, it was not available on the R2. So, it was only available at R1 during the shift operation. So, the update DR operation, this value is available at R2. As a result, the value is available onto this particular pin. Now, this pin being so now this circuit. So, this is mode put in captured DR mode. So, from the input, it from the from this input. So, it is getting captured onto this cell. Okay. So, these cells R1, it has got this value now. Now, this has to be transported to this output. So, how that is done? So, that is done in this fashion. Now, this chip 2 is put into shift DR mode. So, this R1. So, through this R1 line, all the this R1 inputs, R1 register values, they get shifted into through these registers, and they come to this TDO. So, all these are done by the R1 line. So, that way we can get it onto the that serial outline of the boundary scan cell that is coming here, and that is finally connected to the test data output for the entire chip. Okay. So, that way this is in the 3 steps. So, this can be done, this X test execution. First, the chip is this first chip is put in the shift mode, then the first chip is put in the update mode, and the second chip in the capture mode, and in the third phase the second chip is put into the shift mode to finally get the shifted value at the output. Now, the in test instruction. So, now here what is happening is that some test pattern that is coming through this TDI line that needs to be applied to the circuit. So, first it is this tap controller will put the shift D, it will put it in the shift DR state. So, this shift DR mode. So, this test data that is coming to the TDI line. So, they get shifted into these R1 registers of this of the boundary scan cells, and after that it goes into the update data register mode. So, it is assumed that this particular operation, it requires a certain pattern to be applied only at on this line. Okay. Only on this bit I need to put some special value. Rest of the bits for the internal logic, they are assumed to already have assumed some values, only another bit has to be sent. Maybe those values were obtained from say by normal operation that okay. So, normal operation, the bits got transferred there and all that, only this through sample operation, and only via one bit we need to transfer, that one bit transfer is taking place. So, this shift operation, that bit comes to the R1 register of this particular cell, okay, R1 register of say this cell, and after that by update DR, this R1 value goes to R2 value and R2 register, and the R2 register's content is available at the out pin. So, this outline is now fed to the internal logic. So, this value is available here. So, this update DR, so this test pattern can be applied onto this internal logic now. After that, there has to be capture. So, this value whatever has been applied to this internal logic, so that produces some output. Suppose it has modified several bits, but we are interested to get the value that is captured onto this register alone. So, that way again, so it goes in the capture data register mode. So, that way this value will be available onto the R1 register of this cell, and again there will be a shifting. So, shifting will be going of all these R1 registers. So, they are put onto this chain, and through this shifting operation it finally goes to the test data output pin of the chip. Okay. So, this way I can for testing, for in test, where the pattern that I apply has to go through this logic. So, first the bit is set here by shift operation, then by an update operation. So, it is put on to R2 here, then this is then this circuit operates. After that it goes into a capture DR, where the response of this logic is captured by the at the output cell R1 register, and then at the next point the value will be shifted out through a number of cycles into through this TDO line, through this R1 register forming that SISO, that serial shifting, so it will come to the TDO pin of the chip. So, this way the in test instruction is taking place. So, then next we will look into this boundary scan description language or BSDL. So, this is a part of 1149.1. There are several purposes of it. It provides standard description language for these boundary scan devices, simplifies the design work of boundary scan, automated synthesis is possible. So, basically if there is a language, then the boundary scan designers and this the chip designer who are designing their chips to be compatible with boundary scan. So, that becomes easier. So, consistency in the ASIC design phase, manufacturing phase, foundry and the stage developer, ATE manufacturer. So, all of them they can be unified. It makes it easy to incorporate a boundary scan into software tools for test generation, analysis, failure diagnosis, etc., and it reduces the possibility of human error when employing boundary scan in a design. So, this is a part of 1149.1. It has been introduced in 2001, the boundary scan description language. What are the features? It describes the testability features of boundary scan devices that are compatible with 1149.1. So, it does not try to augment that particular standard, but it only provides a description policy for the boundary scan device. Okay, so, this is a subset of S subset of VHDL. So, S subset is the synthesizable subset. Okay. VHDL synthesizable subset has been used for describing it. System logic and 1149.1 elements that are absolutely mandatory did not be specified. So, bypass register, tap controller, so they are always there. So, they are the mandatory part. So, they need not be specified, only the remaining things are to be specified, like whether the TRST mode is there, reset mode is there, how many internal registers are there. So, those things are to be specified. So, the basic things are not to be specified, and there are some commercial tools that have come up for this for synthesizing in the boundary scan description language that we have. So, if you have some description in that language, the commercial tools are there which can do the synthesis part. So, this is the overall structure, the BIST support, scan and BIST support with boundary scan. Like what can happen? So, this is the entire chip. So, this is the logic that we have. Now, this logic may be tested via some external input, or it may be tested via some BIST. Okay. So, what is done is that this tap controller, so this test access port. So, if you are trying to send some input serially to the scan chain, so through this TDI line you can feed the input into the scan chain, and similarly this scan out line, so that can be connected to the TDO test data output point through this multiplexer. So, this tap controller can do that serial shifting through this scan path, pattern may be applied, response may be captured and all that. So, that may be done. Second thing is that it can, there may be some BIST. So, this tap controller can be informing the BIST decoder like what to do. Okay. So, that way this BIST decoder will in turn tell the BIST controller like whether it should do the operation, if there is a reset signal, clock signal, hold signal. So, they are given to the BIST controller. Then this memory and register file, so they are normally tested by BIST. So, here the logic may also be tested by BIST, but the logic part of the circuit, but it is normally not done, because of the reason that logic part is I should say more heterogeneous across different designs. So, their test patterns will be different, but when we are talking about memory and register files, so they are more regular in nature. So, possibly we can just take help of some regular test patterns for doing this memory register file updation. So, and they are testing. So, the BIST controller can be are normally used for this part, and naturally there has to be some compressor which will compress all these responses, and then it will be selecting the BIST signature output. So, the serial output, so that can be given out of TDO. Now, there. So this tap control, this boundary scan, it will have the instruction register as well. So instruction register, it will go to the decoder. So decoder will tell whether it is a beast instruction, it is an internal scan. So if it is an internal scan, the decoder of this tap controller, so this will tell that, it will inform the scan decoder, and it will tell how to input the scan. It goes, it gives scan enable signal to the scan path. So what sort of operations are to be done? So that is told by the scan decoder. So rest of the things are not shown. There may be some more control lines needed for controlling the scan path, but that is not shown here. Similarly, we have this thing, this beast operation. So if it is a beast operation, then this beast decoder will be informed, and accordingly the beast decoder will be controlling the beast session. So this way we can have this boundary scan, which can support this scan and beast operations in the entire operation. Sometimes we can have bus master for chips with boundary scan. So we can have this type of structure. So ring architecture with shared test mode signal. So here what is happening is that, so these are some chips 1, 2, 3, these are different chips, and you see the test mode signal that is here. So it is common to all the 3 chips, and the TDI line, the test data input line, is going to the first chip, and this TDO of first chip is going to the TDI of second, and that way TDO of second will go to the TDI of third, that way it goes. So these actually forming some sort of a ring structure, all these chips as if they are put on a ring, something like a daisy chain. So if the first, though the test mode signal is given to all of them, this test data input and test data output, so they are actually chained like this. So since the test mode signal is common to all the chips, so all of them will be doing the same operation, all of them will be doing the same operation, but this test data input lines, they are serially connected. So you can put different values onto these data registers, so that they can be operating on different test data, but the test mode line being same, their transitions of the tap controller will be same. So all of them will be going into the same set of transitions. So this way we can configure these chips onto different modes, and these different architectures can be made out of this boundary scan. We will continue in the next class.